Okay, this is a supplemental lesson to lesson 4 using two chemical reactions, one of which is exothermic and one is endothermic. So we're going to start with an exothermic reaction. And remember, these are reactions that give up or release energy. And the first example is the same kind of relationship as the NaOH example, the sodium hydroxide example in lesson 4. So for this one, we're going to look at what happens when you dissolve calcium chloride in water. And the two products are going to be calcium ion aqueous plus chlorides aqueous. And then this is a reaction that releases energy. So we can actually put energy on the product side of the reaction. Now, a few videos ago, we talked about compositional potential energy. So I'm going to remind you of that. So composition, potential energy. And what this is it has to do with breaking and reforming bonds. So you can think of chemical bonds as having potential energy because they store energy. And you can remember from your physics classes and from my class that we define potential energy as energy that's being stored in some form. So chemical bonds can store energy. So what we have going on with our chemical reaction here, we start out with calcium chloride, and that has a really strong ionic bond. We then are going to add this to water. So let me go ahead and draw a diagram of that. Remember that the water in the glass is the surroundings. And then we're going to take the calcium chloride and dissolve it in here. So the reaction is going to be represented by the system. And I will put the reaction in here in a somewhat simplified form. So the reaction is the system. The thing that we're studying is the system. And so let's go back to this idea of compositional potential energy. So the calcium chloride here has a certain amount of potential energy because of the ionic bonds between the Ca and the Cl2. The two products also have a certain amount of compositional potential energy. The products. And what is that composition? It's because of the bonds between the ions and water. You know, if you just step back from this for a minute and you think about what's going on, we're taking this crystalline solid and we're adding it to water. The ions are being separated and then they're bonding to water. That's what this aqueous business is all about. That's what it means. It means these ions have now formed bonds with water. All right, and for an exothermic reaction, the potential energy of the reactants is going to be greater than the potential energy of the products. And if you're wondering then, okay, so where did the other energy go? All right, so if we look at the potential energy of the reactants, this is going to be equal to the potential energy of the products plus kinetic energy. So this sum total right here equals what we started with. Now, what's going to happen is that energy, which is in the form of kinetic energy, when it's released from the reaction, enters the surroundings. All right, and when it enters the surroundings, the temperature of the surroundings will rise. So, to put this in human terms, when you start this experiment, and say you're holding a glass of water in your hands, which represents the surroundings, that glass of water is going to be room temperature, and it's not going to feel much different in terms of how warm it feels and your hands, right? It's going to feel like there's not much difference. But then you're going to add the calcium chloride in there and mix it up. And the calcium chloride is going to dissolve. And when it does, energy is going to be released from the system and enter the surroundings, and you're going to feel that glass of water heat up. It's going to get hot. You're going to go, wow, this is getting hot. And the reason that's happening is because the reaction is releasing kinetic energy, which is entering the surroundings, and the temperature of the water is going to rise. And in fact, if you were to start with a glass of water that had a reduced amount of water in it, and you really bumped up the calcium chloride a lot, you could actually get this liquid to come to a boil. You'd have to literally put the glass down. That's how much energy gets released during this reaction. All right. If we were to represent a graph here of this, and I was to put energy over here on the vertical axis, we would pick an arbitrary place to put the calcium chloride crystal. And the products are going to be represented on a platform that's going to be lower. All right, and we could call this platform E1. This is the energy, the potential energy of the reactants. And then if I draw a line over here, this is going to be E2. So the potential energy of the products is less than the potential energy of the reactants. Now, what I'm going to do is shift to the opposite example. And in this one, we're going to look at an endothermic reaction. All right, and in this case, the example I'm going to use is going to be simple table salt. And again, we have the same, whoops, I need more room. Let me just fix this really quick. Sorry about that. I've got to run that over to the right more. All right. So for this particular reaction, we're doing the same thing. We're taking a crystalline solid that has an ionic bond, and we're adding it to water. And the result is the material is going to dissolve, so that the ions are separated and they're bonded to water. So we have the same situation that we did in the last example, except the energy business is different. So I just want to say here, so over here we have an ionic bond, and over here for the products we have bonds between ions and water. Now for an endothermic reaction, we have a difference, right? Instead of releasing energy, this type of reaction requires the addition of it. So I'm going to write it this way. So we can treat the energy as a reactant. Okay, and remember that the reactants have a potential energy. I'll call that PER. And the products also have an energy, which is PE products, potential energy of the products. All right. Now, in this case, what makes this different than the last example is that the potential energy of the products end up having a higher potential energy than the reactants. So if we draw a picture of this, what's happening? Again, here's the glass of water. And you're holding the glass of water in your hand. And the water represents the surroundings, all right? And inside the glass, we're going to have our system, which is our reaction. And I'll rewrite it here. So we're going to have sodium chloride going from the solid to Na plus Cl minus, where the two ions are bonding with water. Now, in this case, you start out holding the glass of water, and it doesn't feel warm, it doesn't feel cold, it just kind of feels neutral, all right? Then you add the sodium chloride to it, and what's going to happen is you're going to feel the glass of water start to cool down. All right, it's going to get cold in your hand, and the reason that that's going on is because in order for this reaction to happen, as opposed to the last example, you have to have the input of energy. And that energy had to come from somewhere. And where it comes from is out here in the surroundings. So kinetic energy moves from the surroundings into the system. So here's your energy right here, plus Ke. That's what this is. So energy had to come in order to drive this reaction. You can think about this kind of like a car. You know, when you turn the car on, in order to get it to move, you actually have to burn gasoline. So burning the gasoline releases energy that allows you to drive the car. For this reaction, opposed to the last example, we need energy to actually drive it to form the products. Now, if we draw a graph of this, it's going to look different than the last example. Have our energy here. We can put our reactants, just choose a place. This is going to be E1. That just represents the potential, the compositional potential energy where we're starting. And unlike the last example, we're going to finish with a platform higher up. This is where the two ions are going to be. Bonded to water. All right, and if I run their platform over to the line, this is going to be E2. And you can see that the difference between these two things, right? Maybe an easier way to look at this is if I literally draw an arrow. The two products literally had to be lifted above where we started with the solid. It had to be lifted to this new location here, and the only way that that could happen is by the addition of energy, and the energy that was added to this was the addition of kinetic energy. That's how we went from this point to that point. All right. Now, with that, I'm going to go ahead and conclude the supplemental lesson, and I'll be coming back to you onto your screens.